Alright, so last time we were talking about logarithms, we're going to pick up on that. So we're going to continue with section 1.6. The laws I gave you last time are important, so let's just recall them. Logarithms tend to be less familiar than exponentials, so we want to kind of drill this in our heads. So let's start with some of the rules, which I asked you about on the quiz as well. So law 1 was log to the base a of b of c means a to the c equals b, right? So log just provides another way to write an exponential. It basically says that the log of a number to a given base is the power you have to raise the base to get the number. So a raised to the power c will give me b. So that's one law you should remember, and it's actually the definition of a logarithm written in mathematical terms, not English. Okay, so we also have this rule. Log of something to a power is?
And log a.
Right, you can bring powers down. Logs turn powers into products. Read. I have log to the base a of multiplication.
Log a is plus log a 1.
Right, logs turns sums into products into sums, right? On the quiz, I believe I asked if log of x plus y is equal to this. The answer is of course false, because the product is equal to that. And we don't have a formula for the log of a sum, right? So the log of a sum or difference, we don't have a formula for it. So if you see the log of a sum or difference, leave it alone. But if you have a log of a product, you can break it up into a sum. Another law was log of a division gave us subtraction. So it turns divisions into differences. Law 5 was the change of base formula. Rewrite this in terms of a convenient base. Log c of b over log c of a, right? Which later on, what's going to be convenient for us in calculus is the natural log. So you'd be able to write any log to the base a of b. You can think of it as ln of b over ln of a by the same token, right? I can just choose c to be the number e, which is convenient for calculus, and I can think of any log as that. And we can derive a lot of formulas for general logarithms by looking at them this way. So those were the laws we had to know. There were some optional ones, of course. Log of 1 is?
0.
0. Log of 1 is always 0. Take a raised to the power 0, you get 1. Log of 0?
Undefined.
Undefined. Right? Because if a is a positive number, there's nothing I can raise it to in order to get a 0. Right? If the base isn't 0, there's no way I can get a 0. So we have log to the base a of a to the x. This was also on the quiz. That's just x, right? Which we're going to talk more about that today. Logs cancel exponentials. So if you plug an exponential into a log, they will cancel each other. Similarly, it works the other way around. So if I plug a log into an exponential, that gives you x. The exponential and the logs cancel each other. 10 was the fact that log to the base e of a number is the same as ln of that number. And log of a number, we think of that as log to the base 10. Right? So that's just more of a notational thing. Right? So when you see ln, you think of the base as e. So if you see something like ln of x equals y, it's the same as saying e to the y would give us x, right? By this rule. Right? So that's just a reminder of these laws. Of course, we're not going to be applying them in these simple terms. There are going to be problems that we need to solve, and they might not look as nice as these, but the idea is you can use these rules to break things down where you can apply these simple rules to finish them off. And we simplified some things last time, but right now we're just going to look at solving equations with logarithms. See what that's like, which we are going to need in the future. So let's just actually do it. Let's do some examples here. Solve the following equations. A. ln of x equals 7. I think something like this was similar on the bonus quiz. E to the 2x minus 7 equals 10. Let's see. 3 equals 5 times e to the 2x. E to the x squared plus 1 equals 5. So, let's start with part 8. How do you think we do this? Right. One, you can apply the definition. You know that the base here is e, even though it's not written there, because that's what ln means. And we know that this means this raised to that power gives us x. So you can just use law 1 and get e to the 7 equals x right away. Another way you can think about it, which we're going to use, so I'm going to mention it now, is to actually use law 9, right? The idea that if I plug a log into an exponential, they will kill each other. So if I see here a log to the base e, what I can do is I can plug each side into an exponential with base e. So I can take e to this, e to that, right? And you might say, yo, you e both sides is the shorthand what you would say. So you e both sides, this guy would cancel, and you get x equals e to the 7. So you can use law 1 or law 9. Law 9 is a nice way to think about it because it works even in situations that looks a lot more complicated than this. But either would be fine, you still end up with the answer, x equals e to the 7.
ln both sides.
You can ln both sides, similar idea to here. You could also again use law 1. It's kind of just going from this step to that step. But let's look at it as ln in both sides. What that means is you plug each side into an ln, right? So don't think of this as being multiplying by ln. Think of it here as you're plugging each side into an ln, right? The thing is, ln by itself makes no sense. So I don't want you to do things like, oh, divide both sides by ln, something like that. It doesn't make any sense. You have to have log of something. So we're going to take each one and plug it inside the log function on the left side, and you will cancel. That's law 8. Then we'd just be left with 2x minus 7 equals ln 10. Now ln 10 is just a number, right? That's the number that when I raise e to, I get 10. That's what that number is going to represent. And so now I solve for x, which is add 7 to both sides. Then divide both sides by 2. Another thing, you cannot infiltrate the log, right? I can't divide this 2 into the 10 or anything like that, right? What's inside a log stays inside the log, right? The only thing that we can move outside a log is a power. That's by the second law. You can't multiply something inside an ln, so be aware of that, right? ln is kind of like trig functions. We don't have trig in this class, but it's sort of the same thing. Just as how sine by itself doesn't make any sense, and if you have sine of x and there's a number out here, you can't multiply it in. It doesn't work. Okay, what about this one? What about 5? Sure, we want to get to the x, which means we want to isolate it, so we start getting rid of everything, right? So here's a 5 hanging out, has nothing to do with the x. Just move to the other side, divide both sides by 5. Now what? Now you ln both sides. So on this side, ln and e cancel, you just get 3x. On this side, add ln of 3 over 5. Then
Divide by 3.
divide both sides by 3 to solve for x. Again, this 3 cannot divide into that, so resist the temptation. You can't go inside the ln. That would be your answer. Now, of course, if you plug this into your calculator, you'll actually get an answer, but calculators aren't allowed in tests or quizzes in this class, so that's how you leave your answer, with ln or e's in the answer. Ready now?
Can you take the log base 2?
Log base 2. Notice here the exponential has base 2. So if I want to kill a base 2, I can use the log to the base 2. So I log both sides, base 2. On this side, the log kills the exponential, and I have x squared plus 1. On that side, I have log to the base 2 of 5. Then,
Subtract 1.
subtract 1.
And square root.
Right, there are square root both sides. Is that fine?
So you don't subtract 5 and 1? It stays like that?
No, because again, this is
Okay,
the
that's
log
far
of
from the
5.
log.
You can't
Okay.
move it inside.
Makes sense.
Right. So think of this as being inside the log. The 1 is outside the log. You can't move it on the inside. Remember, when you're radical, you plus or minus, unless there's for some reason that you can't take the minus. But in this case, we can. So you could leave the answer like that. As well as what you can notice is that we can use logs, any log that's convenient for us. So for example, you'll notice that log to the base 2 is actually not in your calculator. There's no reason why we had to use log base 2. I used it, when you're writing by hand, it's nice to use log base 2 because it gets nicer, you just killed the 2. But you could have also, if you're doing this in your calculator, for example, you could have ln both sides. Now there's a law that says this guy, I can actually bring down. So that's ln of 2 equals ln of 5. And I can say x squared plus 1 is equal to ln of 5 divided by ln of 2. And then I can again subtract 1. And then I can square root both sides. And that is also a valid answer, right? I can use any log I feel like, actually, right? In this case, when you're writing by hand, you use log 2 because it's just nice. You don't have a division of logs, you just have a single log. One thing I want you to notice is that this guy is equal to this guy by the change of base formula. Law 5 tells us that this is the same. So if you, for example, you're practicing in your textbook and you do it and you get this answer, but the textbook, the answer in the back looks like this, you should be aware that, oh, it's really the same thing. Right? So you can, the logs, the change of base formula, law 5, will show you that this and that are the same. If you want to plug something like this in your calculator, you'll use that form. Because your calculator has ln and it also has log to the base 10. So if you have a calculator on hand, you'd want to use ln or log to the base 10 because that would work in your calculator. By hand, though, you could do something like this. One other thing I'd like to mention here is, how do we know that answer makes sense? What do you mean? Well, it is a radical, right? Which means it has a domain. What do we need for a radical? Where does a square root work? Underneath the radical must be greater than or equal to 0. So I ask again, how do you know that this answer makes sense? How do I know that this is greater than or equal to 0? we're not allowed to use calculators. So it means when you're in a test and you write down this as your answer, you have to know, did I make a mistake? Does that make sense? You have to sort of look at it from that point of view. And so how would you actually figure that out if you don't have a calculator on hand? Well, first consider the log. Log to the base 2. Can you give me an estimate for this? Can you tell me something that you're for sure know that it's bigger than? You definitely know it's bigger than 2. How do you know it's bigger than 2? Right, because I know that log to the base 2 of 4 would give me 2. Right? So if I raise 2 to the second power, I get 4. Now to get 5, which is a number bigger than 4, I'd of course have to raise to a number bigger than 2. Right? So I know that this is definitely bigger than 2. Right? And that would of course mean that if I take log to the base 2 of 5 minus 1, that's definitely bigger than 1, which is bigger than or equal to 0. So it makes sense. Right, so the square root actually works here. Right? So it's not a matter of, oh, there's actually no solution. This solution actually makes sense. Right? But you have to know that without using a calculator. So sometimes you have to know how to eyeball things and how to estimate a log. It would be harder to eyeball this one, but I guess you have to be really confident that you know what you're doing. Any questions on those? Solving equations with logs and exponentials. One important takeaway here. When solving equations, to get rid of an exponential, use a log to the same base. Right? So if what you want to solve for is in the power of an exponential, use a logarithm to get rid of it. Right? So you had e to the 2x equals 5. Right? Here, I want to get to that x, which means I have to get rid of this exponential. How would I do it? I'm going to use a log to the same base. In this case, the base is e, so I ln both sides. Right? So you ln both sides. Which we did an example like that already. And of course, vice versa, to get rid of a log, use an exponential to the same base. Okay, so if you see something like, you write e2 is 5, here, you would ln both sides. Or if I see ln of x plus 1 equals 7, here I would e both sides. Right? So I want to solve for that x, I need to get it outside of the ln, exponentiate both sides. If I have an exponential, I don't want to get the x in the exponential, ln both sides, right? So logs get rid of exponentials and exponentials get rid of logs. That's what laws 8 and 9 were about. So if you're solving equations and you want to kill one or the other, use the opposite. Which, by the way, that now leads us to the graphs. Which I told you I'd tell you about this time. So let's actually look at those. Laws 8 and 9 show us that y equals log to the base a of x and y equals a to the x are inverse functions. Right? Remember, inverse functions are the ones where if you plug one function into the other, you get the original input. Right? So if you take f of f inverse of x, you get x, or if you take f inverse of f of x, you get x. Right? You plug one function into the other, you get the original input. These are called inverse functions. So, do you remember what y equals a to the x looks like? Right? What does y equals a to the x look like? Assume a is bigger than 1. Right, looks like that. What is the intercept here? 1. Right? So you know that's what it looks like. So to find this inverse graph, how do you find the inverse of a function? The graph anyway. Remember how you algebraically find an inverse function? You switch y and x, and you solve for y, right? So the x values become all the y values become the x values. Graphically, what happens? That means a reflection in the line y equals x. So I'm going to take the line y equals x, and I'm going to mirror this over it. What I end up with is a graph that looks like that. That passes through 1. So if this is y equals a to the x, then that guy is actually the graph of y equals log to the base a of x. And so that gives us the graph. Which was a bonus problem on the quiz, is to draw the graph of a logarithm. Basic graph of a logarithm looks like that. Notice, it approaches 0, but it never actually touches it. It keeps getting closer and closer to 0, but never touches it on the x value, right? That's because log of 0 is undefined. You'll never actually hit 0, right? But it can get as close to 0 as you want, and it'll just keep going, right? So you say, in the language that we'll use later, that x equals 0 is a vertical asymptote of the logarithm. We'll talk about asymptotes later, but that's what the base graph of a logarithm looks like. So a very important graph to know. You need to memorize that graph. It's one of the basic ones you need to know. Sort of like y equals x squared. Everyone should know what y equals x squared looks like. In the same way, you need to know what this graph looks like. It's just something we know now. We know what L is, right? And every log will look like this. The only difference is the steepness will change. So log to the base 2 of x, ln x, log to the base 10, log to the base 17. They all have this basic shape. The difference is the steepness, and if you're sketching by hand, you will notice the difference anyway. So that's the basic shape of it.
Excuse me, that's the same graph for Ln?
Yeah. Right. So it's just that things will be steeper, right? So you can have another graph that looks like that, or another one that looks like that, right? Depending on the base, it can be steeper or shallower, but that's the same basic shape. All logs will have that same basic shape. Of course, just like with any other graph, transformations apply in the same fashion. So for example, if I were to graph y equals the negative of log to the base a of x, that will just flip this in the x-axis, so that would look like this. Or if I wanted to graph y equals log to the base a of minus x, that would flip in the y-axis, it would look like this. And so on and so forth. I can flip them, I can stretch them, I can shift them, just like any other graph, it'll work. But knowing the basic graph is very important. It'll help us with not only graphing, but also with limits, which is going to be one of our next topics. Okay, so that's the graph, know the graph. let's see, we went through the 10 rules, the graphs, numbers, we solved those equations, simplified that, we solved the equation. Okay, so that's it. We're done with section 1.6, which means we've done with all the material needed for the first test. So test 1, which covers 1.1 to 1.6, will be on Monday. A week from today. Or we can make it Wednesday, 9:28. Any preferences? I don't particularly care. Let's make it for Wednesday.
Yeah, Wednesday.
In either case, I'm going to grade it on the weekend anyway. So even if I give it Monday or Wednesday, it's not being graded until Saturday, so I don't care. So we can make it for Wednesday. So that will be test 1. It'll cover all of this. The review for test 1 already posted. So go through that. That's the link I gave you in the syllabus for this class. Also, homework is finally up for those of you who didn't know about it. I think the homework is due it's probably due on this day.
It's due this Wednesday.
I don't think all of it is due.
No, just one. The orientation one.
Right, but the other one is due on the 26th,
Yeah.
right?
Yeah.
Which is good, so you have time to ask me if you have any questions on those. So, web work homework is up. So far there are 4. There's an orientation which basically walks you through how to use the system, how to type things in, how to use the templates. There's an algebra review, almost everything we need from algebra, but it was getting too long so I had to stop. Tons of problems there. But a lot of them are just really quick questions where you can answer in a couple seconds, just checking some basic ideas. But yeah, they're like 100 or something. You do like 10 per day, you'll be fine. Right, and there's a homework on exponentials, which is the first topic we seriously reviewed, and logs. So you can check that if you really understood what's been going on in class the past couple lessons, right, you should check those, make sure you can do them. So it's up now, and
You said 2 of them are due on Wednesday?
I think these 2 are due on Wednesday. I can push everything to the 26th. I can change the date if you want. But I think it's good to have them done by at least the 26th, so you have a couple days, if there's anything off. You can see me on Tuesday or earlier Wednesday and try to get that sorted out. But yeah, so first test, that day, only these sections.
The entire class time for the test?
No. Test will be, I think, 1 hour, 15 minutes. About 5 problems. Of course, there will be several parts each, but. So we'll cover things like algebra. So we'll cover things like some algebra concepts, simplifying, factoring. Graphing, etc. It'll cover the difference quotient, how to plug something into the difference quotient and simplify it. We'll cover, of course, exponential and logs, both simplifying and solving equations. Of course, like straight lines. I'll have to finalize the test. I didn't finish everything yet. But off the top of my head, those are some things that I know are going to be on it. So pretty much everything we've done in class so far. Go over the quizzes, the answers. Well, the answer to the quiz that I gave you tonight, I'll try to post it tonight. So you have all the quiz and all the answers, and you can practice, do the homework, do the review. And if you can get through everything reasonably well, you should be fine.
And the questions you assign is a good help, good practicing, right?
If you go through the review and the homework, you should be fine if you can get them. The only thing is, it's that you will feel a time restriction, so you want to get them and be able to do them fairly quickly. The timing will feel a little tighter than the quizzes, so if you always run out of time on the quizzes, that means you need to tighten up. If you get through the quizzes before I say time's up, you're kind of fine by time-wise. You just need to actually memorize all the formulas you need and all that sort of stuff. Any other questions? Yes? Yeah, there's some in the review. They'll be the ones where you try to set up a model, sort of like the hot dog problem or something like that we did. There'll be not a lot, maybe one part of one question you can just set up some of the problems. For the most part, I'm testing your algebra and how to simplify stuff. There'll probably be one word problem on it. Any other questions? I'll probably talk more about it later, but now you know. I'll leave this up for a little bit. So that's pretty much chapter 1. Now we're going to move on to chapter 2, which means we're actually going to start calculus finally. Start with 2.1. Actually, nothing special about 2.1. We've already sort of beaten this one to death. Measuring rates of change. Is what this was about. And I already sort of planted the seeds of this idea. Slope is where it's at, basically. So main ideas in this section is slope, which is something I have mentioned to you before, can be used to measure a rate of change. In particular, how fast a dependent variable changes with respect to an independent variable. Right, so keeping things a bit general here, your dependent variable and your independent variable, it's all based on context. It's based on how you set up a function to solve what purpose. I illustrated this with choosing the dependent variable to be distance, while the independent variable was time, and that's how we got miles per hour, and that's how we kind of got the speed. But again, these could be anything that we choose to apply our function to. And so it didn't have to be miles per hour. It could be population with respect to time. How fast is this population growing? Or how fast is this radioactive element decaying? How fast is the growth of a tumor growing? Things of that sort. You can apply these variables to anything you're tracking with a function on a graph. Right, so slope is a way that we can measure rate of change. That was the first main idea that they talked about in this section. And the other one was they actually gave us a formula for the average rate of change. which I think I also mentioned on your quiz. I told you that on your quiz. As it turns out. The difference quotient gives us a way to find the average rate of change. Good. So basically what that says is let's say I have a function doing whatever, y equals f of x, and on some interval, a to b, I want to find out on average how does the independent variable change with respect to the dependent variable? Well, the idea is, I know in the between it can rise and fall and do whatever, but I only care about average, so I can connect these with a straight line. And then the slope of that line is going to tell me the average rate of change. Overall, it will tell me how the rise changes with respect to this run, overall, on average, right? So that's sort of how we can measure an average rate of change. So this means that f average is how we call it. It would be, here this is a, that means that would be f of a, and if this is b, that would be f of b. So it's y2 minus y1 over x2 minus x1. Have the average rate of change is this. So this is the average rate of change of f of x from x equals a to x equals b. B is the larger number. So I want to figure out how much did it change on average between points A and B, where A is the starting point, B is the ending point. I can actually use the difference quotient. I can use this formula. I'll give you an example, but before that I just want to show you that this formula is actually equivalent to the other version of the difference quotient that we have. Note, this is equivalent. However, usually when I ask for this, find the average rate of change, just use this form. Equivalent to the other formula for the difference quotient. So the idea behind that one is it's just a matter of labeling things differently. So that's the x-axis. I can call this our initial x value, and I can call this the new x value x plus h, meaning from the original value I moved a distance h to get to the other value. So this one here will be f of x, and the corresponding y value here will be f of x plus h. And so I can think of the average rate of change also as y2 minus y1 over x2 minus x1. I get f of x plus h minus f of x over x plus h minus x. And of course the x's kill each other, and I would have f of x plus h minus f of x over h. And So that's where the difference quotient came from. It's actually a slope. It's the slope of a function between 2 points is the difference quotient. It gives us the average rate of change because the slope can used to measure rate of change. Let's do an example. Okay, what is A and what is B here?
A is 3.
A is 3. The left end point of the interval, that's the starting point, and B would be supposed to be the other one, 6. So here, if I wanted to find the average rate of change on 3, 6, that means between x equals 3 and x equals 6. The formula would be f of 6 minus f of 3 over 6 minus 3. And f of 6 is
36.
36. I just plugged 6 into that function I was given. So this is 6 squared minus 3 squared over 6 minus 3. So this is 36 minus 9 over 6 minus 3. And 36 minus 9?
27.
27. 6 minus 3 is 3. What is 7 over 3?
9.
9. Right? And you think of that as the average rate of change. So you can see here what this number means on average. The y value changes by changes here I can emphasize any increase by 9 units every time the x value increases by 1 unit. Right? That's how you can think of it. How fast is this guy changing with respect to that guy? Right? Every time your run moves by 1, your rise will move by 9 on average. And this is an idea we'll come to later, but how do I know it's increasing is because the answer is a positive number. So positive F average means it's increasing overall. On average, negative F average means decreasing overall. That means the y value is getting smaller every time the x value is getting larger. So this is just talking about how the y value is moving on average. So if you look here, if we actually look at the graph of y equals x squared, I plug in a 3 and a 9, I go from this point to that point, and 6. This is a 36. This would actually be a 9. So what I've actually computed was the slope of the line connecting these two. And on average, every time I move over 1, I would move up 9. That's how you want to think of it. Right? So overall, if I move over 3, I'll actually move up 27. Right? Every time the x increases by 1, my y will increase by 9. And that's how you want to think of it. Right? This is just on average.
So it's just for that section and
Yeah, I only care about that section. So average, I have to actually give you an interval. Here, I gave you 3 to 6. Right? On some other interval, it might be doing something else. Like over here, you'll notice that it will be decreasing. So I'd get a negative. Right? If I went from -3 to 3, I'd actually level off, but I wouldn't have done it. Right? So the answer will depend on the region of the function that you're looking at in general. Right? So for this section, between 3 and 6, on average, it will increase by 9. You'll notice that if I change 6 to something larger, it'll actually increase by more. Right? So the answer does depend on what your A and B are. Any other questions? Yeah, so that's the main idea we need from 2.1. Slope we can think of as a rate of change, and to actually have a formula to compute it, it's the difference quotient. F of B minus F of A over B minus A gives us average rate of change. Now going to 2.2. Limits. Let's see how far we get with limits. A little over 20 minutes. Any questions on this before we move on? That's one formula. That's basically all you need to know from 2.1. I already sort of laid the groundwork for all the ideas that we used there, so there's not really much more to talk about. But now we're going to talk about limits, which is a very super important topic in calculus. So remember in lecture 2, when we were talking about what calculus was, we mentioned that it was really the mathematical attempt to understand two kinds of problems: the rate problem, how fast something changes, and the area problem, how much space something takes up, right? And the applications of these two ideas. And I told you that the main tool to figure out how fast something is moving is called the derivative, which is actually in section 2.3. We won't get to that today, but we'll get to it soon. And the main way to figure out how much space something takes up, or how much area a region of a function will take up, is called the integral. It turns out that both of these are limits. You can define them in terms of limits. So if I were to say what calculus is in one word, limits. Calculus is about limits. It's the study of limits. Right? So now we're going to talk about what limits are. Not in all their gory detail, but just good enough to get a conceptual idea of what they are and to do some algebraic manipulation of them. The main idea of limits, getting close. Right? So limits are about getting close to something. So we're going to make this more precise. So one thing you want to think about is limits. It's about getting close to some point. You may not ever actually get there, and that's okay. Just need to get close enough. It's the ultimate demotivator. So now let's talk about what a limit is. I like doing the definition where I introduce the notation at the same time. And say that the limit as x approaches a of a function f of x is L, and write so that's the language we'd use to describe a limit. Here's the notation, how we'd actually write it down. LIM, short for limit. X, you write a little arrow, and A. Beside it, you write the function f of x, and you say equal L. This is the limit as x approaches A of the function f of x equals L, is L. If, when x gets close to A, the function, the y value, y equals f of x, gets close to L. i.e., the limit is the y value, the function gets close to when x gets close to A. Right? So a limit, we're tracking the y values and we're kind of seeing what they're getting close to. It's basically what a limit is. And in this section, in section 2.3, we're going to find out why we even do that, what's going to be the use of doing that. But that's basically what a limit is, right? So we write this symbol down, and it means that as my x gets close to A, my y value will get close to L. And believe it or not, close seems like a relative term. Not everyone would say, oh, what do you mean close? Some people might think, oh, this is close. Other people are like, that's not close, this is close. Or other people are like, ah, that's not close, this is close. Turns out there's actually a rigorous mathematical definition for what closeness means, but we don't care. Math majors care about things like that. In 205, we are not going to care about the precise definition, and we'll all rip our hair out if we actually go there. So it's kind of taken to be an intuitive meaning. I'm going to tell you to what degree or what depth you need to know this here. So that's basically the idea. Limit is the y value you get close to when your x gets close to something. Think of it that way. Right? So let's do an example. Let's start out pictorial. So if I say here, what is the limit as x gets close to 2 of this function? Function 1 is close to 3, 2, 5. Alright, so here's some random function that I just made up, and actually this question. Right, so y equals f of x. What is the limit as x gets close to 2 of that function? 5? Why do you think the answer is 5?
It's in L the y body or something like that.
Mm-hmm. So what does that mean?
And the y 5 is within the y bodies.
Okay. So the idea is that is correct, right? If we're on this function, right? As my x value gets close to the x value 2, right? As my x value gets close to here on the graph, the y values will be doing this, moving towards this point. If I'm getting close to 2 from the other side, my y values will be moving closer to this, right? So it turns out as I close in on 2, my y values will close in on the number 5, right? So in this case, I can say the limit as x approaches 2 of our function is 5. When my x gets close to 2, my y values get close to 5. Okay, what about this one? 2. My function is undefined here. Question, what is the limit as x approaches 2 of our function? What do you think the answer is here? Yeah, but I'm undefined at 5. What does that mean?
There's no limit.
Limit as x gets close to 2 of our function here is
Negative infinity to positive.
this is way off. You're off from the answer by an infinite amount. It's not undefined. Turns out the first answer was right. It's still 5. Why?
It's never exactly.
Because getting close to something is what we care about, not actually getting there. I don't actually care that I can't be at 5. I just want to know if I get close to 2, what do I get close to? The y values will get close to 5. They can never actually hit 5. I don't care. I just wanted to see what are the y values getting close to, right? Limits are about getting close to something, approaching something. Whether or not you actually get there is irrelevant. You just want to know how close are you getting. Now, as I keep getting close to 2, my y values, again, keep getting close to 5. They never actually get to 5, because 5, there's a hole, but that doesn't matter. Limits don't care about being there. They care about getting close to there. Okay? So that's what I mean in the intuitive sense. Getting close to something means you don't have to actually get there. Just get close enough. Right? For all practical purposes, we can see as x is getting close to 2, our y values are closing in on 5. Okay? Here's another one. What is the limit as x gets close to 1 of this function? That one's shaded here. Yeah? Why do you say it's undefined? That's defined.
It doesn't exist in limit because you have to. Like there's 2 different answers.
I know there's 2 different answers.
So they're both approaches from one side and then they're approaches from the from 0 to 1 and from 2 to 1. There's different equations.
Okay, so let's look at closing in on 1. You said different sides, all right? So what if we're on this side? Okay, x is getting close to 1. What's the y value getting close to? 2. Okay, what about closing in on this side? I'm on the graph here. So this is close to 5. So is the answer 2 or 5?
Don't we have different domains because on the first slide?
No, this is one function. This is just how my f is defined.
Oh.
Think of it as a piecewise function. For x less than 1, it's defined as one graph. For x greater than or equal to 1, it's defined as another graph. Yeah? Right. It turns out here, neither is the correct answer, right? One way we can look at this is remember that the limit is the y value. It's important to have a unique answer. I need to get an answer, right? I can't just say, well, sometimes it's 2 and sometimes it's 5. Well, I could say that, but I have to be very specific in my language. It's going to be very important for us to know what's happening to the y values exactly. And so, in this case, I couldn't say the answer is 2 because it's not true that when I get close to 1, I always get close to 2. It's also not true that when I get close to 1, I always get close to 5. It's neither answer would be correct. And I can't really say it's both, because if I get close to 1, I don't get close to both 2 and 5. I only get close to 2 from this side, and so on and so forth. And so what we need here other definitions. This brings us to the idea of one-sided limits. And here's the notation. This notation, I write limit as x approaches a, but in the power, I put a minus sign, right? And then I have limit as x approaches a, in the power, I put a plus sign, right? Now when you see a little minus sign in the power, what that means is the limit as x approaches a from the left. Right, so I'm putting directions on my limit now. I'm approaching a from the left. The negative means I'm a little less than a, right? So I'm coming from the left side, right? Whereas this talks about the limit as x approaches a from the right, right? So it's a plus something. I'm a little bit bigger than a, so I'm on this side approaching a from the right, right? So in previous example, which is this guy, I can say the following. The limit as x approaches 1 from the left of my function is, right. So now I look at this function, I zoom in on 1, but I don't look at approaching from all directions. I only look approaching from the left, right? So I'm only on this part of the function here. Ignore that part. I only care about what's to the left of 1. And so I'm on this function. As I get close to 1, my y value gets close to 2. So I can say the limit as x approaches 1 from the left of f of x is 2. I could also say the limit as x approaches 1 from the right, and I write it like that. Okay, so now I zoom in on 1. I only want to approach from the right, ignore the left. If I'm approaching from the right, it means I'm on this side of the function, traveling, 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 and then my y value is getting close to 5. So the answer here would be 5. Note, and here's how we get the uniqueness of a limit here, just the overall limit. The limit as x approaches a of f of x only exists, right? It only has an answer if both the limit as x approaches a from the left exists and limit, it's not correct, these words, limit x approaches a from the right of f of x exists and they are the same. Otherwise, we say limit as x approaches a of f of x does not exist. It's another way of saying undefined, but for limits, the language that we usually use is does not exist. Or you would write D and E. So in the previous example, that guy way over there, the limit as x approaches 1 of f of x does not exist. Right? So the first answer was correct. So there's the idea of a one-sided limit where you approach things from one side at a time, and those can actually give you answers. But the overall limit will only exist, this guy will only exist if both sides actually connect. They give you the same y value coming from both sides. Right? So as you can see from the previous graphs that I was doing, when I was approaching a certain x value, both y values was approaching the same y value. Right? So whether I came from the left or the right. So we actually need that. If that doesn't happen, we say the limit does not exist. That's the thing that breaks a limit. If the left and right sides do not agree, right? Whether I'm defined or not at the actual point, I don't care. It's just a matter of do the left and right sides connect and get close, and that will determine whether a limit exists or not. So one-sided limits, very important concept. And whether or not a limit exists. Note. It's possible for any one or all of them to not exist. So I can give you an example. Look at the graph of y equals ln x. And I could ask you, what is the limit as x approaches minus 1 of f of x? Obviously it does not exist, right? Because over here at minus 1, there's no graph, right? There are no y values. I can't track something that's not there, right? And of course, it will work for both sides as well. As I approach minus 1 from the left, it does not exist. If I approach minus 1 from the right, it does not exist. Right? So it could be a case where none of them exist, because it just doesn't make sense to track the y values at that point. I could say something like, again, y equals ln x. And I could ask about the limit as x approaches 0 of ln x. As x approaches 0 from the left of ln x. Limit as x approaches 0 from the right of ln x. What about from the left? So if I'm approaching 0 from this side, what's happening to the y values? Doesn't exist. There are no y values. The graph isn't over on the left. So this does not exist. What about approaching 0 from the right? Right? So if I'm getting close to 0 from the right, what's happening to the y values?
They decrease.
They decrease. They keep decreasing. How do you think we'd say that? Yeah? The y values?
But doesn't it stop at 1?
No, the y values keep going down, no, it passes through 1. But if I look at the y values, right, like here, the y value is this. Here, the y value is that. Here, the y value is that. It keeps going down. I can actually say that's a negative infinity. We won't get a lot of time to talk about infinite limits right now, but that's an idea that we'll come back to next time. So what about this one? Limit as x approaches 0. Does not exist. Why not? These two don't match up. Right? That's it. I don't care what they say. If they're not the same thing, this guy won't exist. Right? So we'll talk about limits more next time, and we'll talk about limits at infinity and limits going to infinity and all that stuff. But right now, just try to wrap your head around the idea of approaching something and being okay with not getting there. And we'll do many more examples next time. Limits is a big and important topic. And We're actually going to use it in 2.3 to develop the derivative. So again, homework is posted on WebWork. Make sure you can log in if you can. See the help desk on the first floor of this building during their office hours. The test is on Wednesday the 28th. It covers chapter 1, 1.1 through 1.6. Review problems are on the website. Yes, we have a quiz on Monday. So the quiz on Monday will cover everything that we did so far. Limits will not be on the test though. I'll put it on the quiz.